Hello, my name is Stephen Heitch, and this is my lab 4 on oscillations. As our general outline, we'll go through the introduction, the main physics principles, experiment and data, the code and predictions, some comparisons and errors, and our final results. For our introduction to this lab, our purpose is to understand oscillating motion and to show that the energy principle holds true. Our main concepts, Newton's second law, gravity, spring force, and the energy principle. We will use a glow script of the spring mass system to make predictions about what should happen and then compare them to what did happen with the tracker data. We will see that the energy principle is satisfied in this case, and the motion of the spring mass can be modeled fairly well. So for the main physics principles in this lab, as our forces, we're assuming there will be nothing except for gravity and the force of the spring. Using Newton's second law, we can then predict the motion using it in its form of Vf equals Vi plus F net over m delta t. And then we can update our position using Rf equals Ri Vf delta t, because we'll use Vf for a non-constant spring force. Spring force is negative Ks L hat, so we'll point in whatever direction specified by S, whether S is compression or extension. And then our assumptions is there's no other force and the mass of the spring is negligible. And for the energy principle, we're assuming that the system is the mass, the spring, and the earth, so there should be no external work. So our delta K plus delta U gravity plus delta U spring will equal our work, which will equal 0, which will also equal our change in energy. So for experimental data, mass was attached to a spring, it was lifted to the side and then dropped down, and the trajectory was filmed, and we exported that data to tracker. We get this graph of our positions as for the path to where it went. So for our initial conditions, the x and y values of the fixed end of the spring were set to 0. The mass was moving at a speed vi, which we calculated using our first two data points, found to be 0.277 and negative 0.249 meters per second in x and y respectively, and we're ignoring z because it doesn't move in that direction. So for our code and predictions, we set the initial conditions of the spring and mass to the exact same as that of the real world. So our g is 9.8, our spring constant was 6.87 according to what we could find, and our relaxed length was 0.127. Again, according to our calculations, we set our delta t to the same step as our frame rate on the camera. And then we told the code to iterate, updating the positions and the mass by updating the forces, and then update the energy values as well. So that's what all of this code here does. So this is what we got as our output to this function. It just moves around, following very closely to the trajectory of the red ball. So for our for what we see when we got through is when it iterated, it worked the exact same way with our initial conditions, and we found these two graphs. So we see that the y position is slightly offset but fairly close, although much larger than that of the real experiment, because the real experiment is in red. And for the x position is very close. They are lined up correctly, but it moves more in the x in our model than in the experiment. So for what does it mean? In this example, the energy principle is satisfied. That's because, as we can see on our graph, that orange line is at 0, and that is our delta E. So we see that our delta E is 0, so there's not energy going into or out of the system, and we expect that there shouldn't be. So this is all good. Because the system is defined to be the mass, spring, and earth, and there are no external forces, again, it should be 0. And this is exactly what we see. And then looking at the peaks and troughs of the previous graphs, we would estimate that the system has an oscillation in the x direction with a period of 1.645 seconds. And on the y data, we see that it comes out to 1.535 seconds. So you can see there's a difference, and this is likely due to gravity, because gravity is pulling down on it in the y direction, but doesn't have any effect in the x direction. So some errors that we could have seen was the quality of the video and the frame rate, which might have forced us to use a bigger time step, which might resolve some small inconsistencies in our code. And then we are also ignoring air resistance, the mass of the spring, and other forms of resistance, which could have slowed the mass down, which would also explain why ours are lined up, but not the same. So as our results, we see that generally the energy principle held true. It did, in fact, come out to 0. And the computer seemed to model it fairly well, with some minor inconsistencies. And a better quality video could help fix some of these things. although it's not a guaranteed fix. All right, thank you very much.